So there is no me, and there is no oat milk. We are one.
We are one.
We are the same.
We're just stars, Matt. Welcome to AirSpace from the Smithsonian's National Air and Space Museum. I'm Emily.
And I'm Matt. Twinkle, twinkle, little star, how I wonder what your life is like? Astronomers have long known what stars are made of, and at least the basics of how they live their lives.
There's a main sequence, how an average star lives its average life. And then there's really big stars and really small stars that don't follow the same rules.
We talked to one of our astronomy educators to get the hot goss about brown dwarfs, the tea on neutron stars, and, everything in between. We're walking through the life of a star today on AirSpace, sponsored by Lockheed Martin.
Matt, I think I was the one who has been pitching stellar evolution for a while here for AirSpace, but it's taken a while for us to figure out how to make that sound cool to everybody, because stellar evolution doesn't sound like a thing that everybody would be excited about.
Yeah, we've touched on it a bit. We've touched the sun, for example, not literally, obviously. But, we've talked a little bit about space weather and the cycles that our own sun goes through, and that's related to its stellar revolution. But today, we're diving into the big story of all the stars.
And our sun is really far away, and our sun is a star. But the rest of the stars are really, really far away. But they're really fundamental to humans existing the way we do, because we are all made out of stuff that came from stars, and all the stuff that surrounds us comes from stars. And I think that's a really cool story to tell, and a really important reason why people should be interested in stellar evolution.
Yeah, that's right. Stars are these incredible engines of energy, right? We take that for granted here on Earth, but they're also these furnaces that forge pretty much every element that's important to our lives and become the basis from which all the material of all of the planets really comes from.
And in order to get all the information on how stars live and die in our universe, we talk to our friend Shauna.
I am Shauna Edson, pronoun she, her. I am one of two astronomy educators here at the museum. So I think of my job as giving people their daily dose of wonder.
So our sun is a star. It's great. We all love it. But it is a kind of an average star. It's what astronomers call a main sequence star, because it goes through that relatively predictable sequence of to be born, live, and then eventually die.
Stars in general, and stars like our sun, begin as a cloud of gas and dust, sort of a loose clump of bits of stuff. And the way that they become stars is gravity. Gravity wants to pull all mass close to all other mass. It's trying to pull things together. So given enough time, even with tiny bits of stuff that don't individually have that much gravitational pull, gravity will start to pull together the bits of stuff in a cloud. They'll start to make clumps. And the clumps get bigger and bigger and bigger. If the clump gets big enough, there will be enough pressure down on the center of it that it'll get pretty hot. If you imagine yourself being wrapped up in like 10 blankets with them all pressing in on you, you'd be squished and you would get really, really hot. So that's what happens at the core of a protostar. Gravity's pressing in, it's getting hotter and hotter. Eventually, the core gets hot enough that it starts smashing those atoms together in a specific way that makes energy. So it's taking hydrogen atoms, smashing them together, and turning them into helium. If you smash 4 hydrogen atoms together in the right pressure and temperature, you will produce 1 helium atom, a neutrino, which is a subatomic particle that's weird, and we don't have time to get into all the weirdness about it. But you'll produce a helium atom, a neutrino, and a ray of light. You'll produce a photon of light or energy. It's usually at the gamma energy level, which is one of the highest energy levels for light. But so you produce helium, a neutrino, and some energy. And when it starts making energy, that is when it goes from just a clump of gas to a star.
And those main sequence stars and all the other stars that we're going to get into in a minute have a life cycle. They get born, the way Shauna just told us, they live and die, and then new stars or other celestial objects like planets, asteroids, black holes, etc., get born out of what the star leaves behind.
So before the first stars happened, it was just stuff floating apart. As soon as we got stars started generating energy. They started generating light. They started fusing together elements. So we had more than just hydrogen and helium. We started to have carbon and oxygen and nitrogen and, all of the things that make up our bodies. Stars were what produced that. And so, when we look out in the night sky, we see stars. When we look at pictures from space telescopes, we see galaxies, which are made of stars. And it is because stars clumped together, started shining, and started existing that we were able to form solar systems and planets and create a space. Life can't form on the surface of a star. It's too hot, too turbulent. But with enough cycles of exploding star, guts clump back together, the leftovers from that clump will also clump together and they'll become planets and asteroids and the other things in a solar system like ours. All of that is because stars exist.
And the thing that makes a star a main sequence star instead of like a brown dwarf or a red dwarf or even a neutron star is mass. When it comes to stars, mass is really the thing that drives diversity among stars. And mass is what leads to the gravity of a star and also its temperature.
With stars, mass determines basically everything. An average star like the sun, the most common kinds of stars are the smaller ones. The sun is considered a dwarf star. It's big compared to us, but it's a dwarf star. The mass of the star determines the kind of life it's going to have. Smaller dwarf stars are very efficient with their fuel. They don't use it up quickly, so they live a really long time and they're fairly stable. More massive stars, what we would call giant stars or supergiant stars, live hard and die young. They tend to run really hot, they burn through their fuel really quickly, and they die in spectacular explosions. So a really massive star is going to have a very different lifespan, much shorter, and it's going to end in a spectacular explosion. A dwarf star like the sun is going to last much longer, much more efficient, and it's going to end in a whimper rather than a bang. But getting back to sort of the full series of the cycle. So you have the cloud of gas and dust, or nebula, from the Latin for cloud. Gravity pulls it down into a clump. That starts the chemical reaction, shining light, that becomes a star. And because a star is doing nuclear fusion, this chemical reaction, it's not burning. It's not combustion like fire that we think of. At the museum, sometimes I'll hear grown-ups say, oh, the sun is a ball of fire. And their 9-year-old will say, no, it's a ball of gas.
No, it's a miasma of incandescent plasma.
Yes.
Ask me how I know.
Thank you. They might be giants.
So all stars, no matter how big or small they are, do spend some time in the main sequence because it's the time in a star's life when it's fusing first hydrogen, then helium. These stars are not all the same. They are different sizes and live for different amounts of time. But so long as they're fusing hydrogen and helium, they are on the main sequence.
Even though main sequence stars are kind of average, they range from about 1/10 the size of our sun to 200 times the size of our sun. And they can live millions to billions of years. But what happens when a main sequence star starts to die?
It's going to start running out of hydrogen in the core. It's been fusing it into helium, so it starts building up all this helium, and there's not as many hydrogen atoms there to smash together. When that happens, it starts putting out a bit less energy. The whole star has gravity pushing in, and it's got heat energy pushing out. For most of the star's life, those things are in balance. So the star stays the same size, and it's stable. When there isn't enough heat pushing out from the core, as that fusion reaction slows down a little bit, gravity starts to win. Gravity starts to smush it down. That then causes more heat as the increased pressure happens, and then it can start to fuse helium into other things. Now, a smaller star may only get to the point of fusing helium into higher atoms like carbon or maybe oxygen. With any star, as it starts running out of fuel, the outer shell of the star, sort of the outer layer, will start to kind of fluff outward a bit. And it kind of puffs up you can imagine a pufferfish. It just sort of fluffs up. There's not more stuff, but it is bigger and more spread out. And that surface will cool. Eventually, as it really truly runs out of fuel, the outer shell will sort of float away and it will become what's called a planetary nebula. Nebula meaning cloud. Planetary, very confusing name. It's because it looks like a planet in a telescope.
And then once that star has died, it turns into that planetary nebula, and the particles that make up the planetary nebula become something else. But this takes a really long time.
And what's maybe not intuitive is for bigger stars, this takes much less time. Stars that are outside of the main sequence, because they're much more massive than our sun, they live much shorter lives and therefore much more dramatic and explosive deaths.
For a star like the sun, that main sequence period is 10 billion years, maybe more, maybe slightly less, but in the billions of years. A giant star or supergiant star, so one that's way more massive, it collected a lot more stuff in that initial gas cloud before it started doing fusion. That would be a star like, say, Betelgeuse or Sirius, which is the brightest star in our sky. These giant stars, they're still fusing hydrogen, but they're just going through their material so fast. A giant or supergiant star is only going to last for a few tens of millions, maybe 100 million years or so. And in context, all of these numbers are big. I can't wrap my head around it. I don't actually know anyone who can. So I want a disclaimer for everybody out there. If you're thinking, oh, I can't imagine 10 billion years, you're correct. I can't either. It's beyond human brain. So that's fine. We're just going to think in terms of relative stuff. So in terms of Earth timeline, the last dinosaurs ended 65 million years ago. So there are giant stars out there that didn't exist when the last dinosaurs died. And that's kind of amazing to me.
I love that. But I love that comparison.
Right. Because dinosaurs are something that we can think of as, okay, long time ago. But yeah, there are stars that we see in our sky now that formed either during the dinosaurs' time or since then. And they're not going to last a whole lot longer than now. Yeah, so it's orders of magnitude shorter life than a sun-like star. So a giant star, like, say, Betelgeuse, it's used up its fuel really quickly. It is fluffed up into the red giant. It's got enough mass. Its core is going to keep fusing heavier and heavier elements. If you picture the periodic table, those elements, as you go down the rows, the elements get heavier. And it takes more and more energy to fuse heavier elements. You still get energy out of those reactions until you get to iron, which is the 26th element on the periodic table. A really massive star can fuse iron. But as soon as you try to start fusing iron into other things, the chemical reaction stops giving you energy and it starts taking energy away. In order to fuse iron, you have to put more energy into that reaction than it's going to take out. So that is going to swallow the heat and energy from that star really quickly. If a star gets to the point of fusing iron, it's got like hours to days to live. It cannot last it's not sustainable because it's
which is like a blink of an eye in
in
the context of how long that star's been around.
When massive stars get to the point of dying, they don't necessarily become things like planets and asteroids. In fact, they can become things very different, like black holes.
With a giant star, you've got enough mass there. You still get the problem where if there's not enough energy pushing out, then gravity pushing in starts to win. When there's enough mass, the core will collapse down and it will suddenly heat everything up. You will get a shockwave explosion that blows outward. So this is your supernova explosion. If it's massive enough, when it crushes down, that sudden temperature pressure change is going to give you this huge explosion. And some of the core is going to get crushed down. It might become a neutron star, which is insanely dense, but at least is like a ball of stuff that has some size. It might be like, 30 miles across or so. So the size of like a large city. If it's even more massive, it'll fully collapse down to an impossibly tiny point, and that'll be a black hole. The rest of the outside part of the star, the explosive force is going to blow that outward. You're going to end up with a cloud of star guts, but a supernova is going to blast it way farther out with a lot more force. It's going to be really bright. So we can see supernovas that happen in other galaxies that are millions or billions of light years away. Those supernova explosions are so powerful and bright. We can see them from insane distances where otherwise we're looking at the galaxy. We can see the smudge of the galaxy. We can't see individual stars, really. So supernovas, within their light, there's information in that light that tells us about that star. How massive was it? What's its temperature? How much energy is that explosion putting out there? And that's really valuable for astronomers.
What happens with small stars? I mean, I feel like small stars are going to get a lot less attention because if mass is what matters, all the exciting stuff is happening to the big stars and nobody's paying attention to the little stars, which makes me feel bad because I'm sure they're also very cool.
Literally cool.
But literally, right? If you have a small star, you have lower pressure, which means you have lower temperature. Mm-hmm. But does that mean your life cycle or your lifespan is a lot longer?
Yes, it does. So we always talk about the sun as an average star. It is on the low end of size and mass. There are quite a lot of stars that are smaller than the sun. So our sun, I think of things in terms of mass and temperature. The sun is sort of a yellow-white star. If you think of the rainbow, the hottest stars are blue. The sort of medium temperature stars are kind of yellowish like the sun. As they get cooler, they get more orange and then red. And again, smaller, cooler stars live longer. The smaller a star is, the longer it's going to live. And so there are red dwarfs that are one of the most common kinds of stars. There's tons of them. They can have lifespans of hundreds of billions to trillions of years. And that is older than the universe is.
I was about to say, I smell something funny.
Yes. So there are red dwarf stars that are still around that have never died because the universe is not old enough for them to have lived out their lifespan.
Because the universe is what, like 15 billion years old?
13.7 billion years old.
I was off by a few billion, but whatever,
You were in there, tens of,
what's
in the
a
teens.
Couple of billion years between events?
Exactly. So there are red dwarf stars that are so efficient and live so long, they can live much longer than the universe has existed.
So if we haven't seen any of these stars die, how do we know how old they're going to get, or when they're going to die, or how they're going to die?
So that is one of those big things in astronomy. We're trying to figure that out. And we don't really get to see stars changing life stage very often. We catch a few supernovas, we'll see them happen, but we don't really get to see a lot of other transitions. We're trying to study the life cycle of stars without ever seeing them change life phase. And I would liken this to if you were far away and you were trying to study humans and figure out how humans develop, and you couldn't watch any videos or anything. You just had snapshot images of thousands of humans at different stages of life. If you just had those snapshots, you could kind of arrange them into a narrative arc. Like, okay, humans start off as babies, and then they start standing and walking, and then they get taller, and then they get kind of pimply and awkward, and then they reach sort of, adulthood, middle age, and then they start to get kind of wrinkly and gray. And so you could kind of construct that sequence of what they go through without watching any one human go through all those phases. So people often ask me, like, how do we know how stars work and evolve? It's because we're able to get these snapshots along the way from different stars and piece them together. And it's amazing to me how much we've been able to figure out from that.
Right. And I think what's interesting is you mentioned that these things could live for much longer than the age of the universe. And that doesn't mean that they were there before the universe. What it means is that we understand their life cycle well enough, we think, that we can actually make a guess as to how much longer those stars are going to live based off of what we know about them.
Exactly. We can model how we know the reaction in their core happens. So we can do computer simulations to say, okay, if it's got this much at this temperature and pressure, how long can it keep doing this reaction? And our models tell us that it can be tens to hundreds of billions of years, if not trillions.
And this is where science and philosophy start blending together. We can know these things, but how can we wrap our mind around something that is so much bigger and so much older than us? And why does that even matter?
Cosmology is the branch of astronomy that deals with beginning and end of universe. Where did everything come from? What was it like right after the Big Bang? How did things evolve to get to where we are today? And what is going to happen to the universe? Is it going to keep expanding? Is it going to slow down? That's all cosmology. Cosmology is based on things we can observe. So big telescopes like JWST and Euclid, the new mission, there's a lot of things we can observe. We can look back in time as far as we can look back, but cosmology is limited to what we can observe and what we can kind of theorize with the math and the computer models. At a certain point, you get into the realm of philosophy of there are things that we can't observe, we cannot see before the Big Bang. So there comes a point where the science can't explain everything, and it becomes more about what does it mean to us as humans. It gives us meaning, it gives us a sense of what's important, of where we come from, of connection across time. There's so many different ways that different cultures and families and, just there's so many different ways to approach it, but it is this fundamental existence as a human creature on this planet to kind of wonder where we came from and what we're part of and what is our place in all of this. And that becomes the realm of philosophy because, it's something that science can't give us, which is fine. Science doesn't do everything. But the philosophy of it and the meaning making of what does it mean to exist as a creature in this universe, I think is really interesting.
So what does it all mean, Emily? You're the scientist. What does it mean for me living on Earth, this little planet orbiting a main sequence star? How does it change the way I see the universe and the way that I live when I go to Trader Joe's to pick up my oat milk? Like, what am I, supposed to do with this?
I think that this is, yes, it's really philosophical, but I think this is a really unifying feeling in that we are all coming not just from the same place, right? Country, state, whatever. I don't think it means that we're coming from those kinds of same places. It means that we're all coming from the same place on a much more fundamental level, right? We are coming from a place that created all of this stuff before Earth even existed, right? Because the Earth isn't as old as the universe, right? The universe is older than the planet Earth. All the stuff that created what we are, where we live, how we live, all of that content, those elements, those atoms came from the life and the death of stars. And for me, that's a really powerful thing because it is, to me, unifying on the most fundamental level. And I think that's really special and a really special thought that I find really exciting to think about how quintessential astronomy and space sciences are to who we are.
AirSpace is from the National Air and Space Museum. It's produced by Jennifer Weingart and mixed by Tarek Fuda. AirSpace is hosted by Dr. Emily Martin and me, Dr. Matt Schindel. Our managing producer is Erica Novak. Our production coordinator is Joe Gurr, and our social media manager is Amy Stamm. A big thank you to our guest in this episode, astronomy educator extraordinaire, Shauna Edson. Did you know that the transcripts of our episodes include citations and extra fun facts? You can find them linked in the show notes. For additional content, photos, and more, follow AirSpace Pod on Instagram and X. We're also on YouTube Shorts. Check us out on the museum's page or sign up for our monthly newsletter using the link in the show notes. AirSpace is sponsored by Lockheed Martin and distributed by PRX. I feel like the show notes is like the syllabus. Check the syllabus, look in the show notes. That's where you'll get all your information.
That's where I get all my exam questions. It's like in Legally Blonde. Always read the footnotes. He likes to get his exam questions from the footnotes. Okay, I'm going to hit the stop button.